If you read the description of the workshop, so I'm gonna focus on kind of what you can do and what are computer interesting for in TouchDesigner. So first we're gonna have like a little overview. And then one of the main interesting use is to kind of manipulate and create 3D textures. And another interesting use is to kind of speed up particle system. And the last example is like a little specific feature on how to use atomic counter, which is a interesting feature. So just to show some like pretty videos. So the kind of funny thing is one of the first thing I tried to do when I was learning TouchDesigner was to kind of create this kind of like 3D fluid simulations. This one is easier, and do some kind of raymarching. Because I was coming from a VFX background, and so it was the thing I was interested in. So that was in 2011, and at the time it was like you could do some things, but it was very slow and not practical at all for like anything more than like little tech demos. And now 8 years later, now you can actually like kind of use it for like this really interesting organic shapes and very different look than what you could do with polygons. So other interesting use of kind of 3D texture. So this example, there's like this fluid field, and the Kinect kind of fits the velocity vector in the 3D texture, and then it kind of gives you like all this nice particle motion. And then besides doing fluid simulation, all the kind of fun 2D feedback system, you can also do them in 3D and visualize them. So this is like a reaction diffusion system. And again, I'm like plug in a Kinect point cloud so I can interact with it. Also, some like things you can do is kind of do this interesting organic shapes, also using feedback system in 3D textures. And another thing we're gonna see. So this is kind of a particle system where like all the particles interact with each other. So it gets heavy pretty quickly because you have n times n interactions. And so some of the computer features kind of allow you to speed that up a little bit, even keeping like a brute force approach without any grid system or more advanced neighborhood search. So now we're gonna. So I was saying I'm sharing this file in case you fall a little behind, but we're gonna recreate everything from scratch. So let's start a new project. We get rid of everything. We create a GLSL top. And so here you want to get rid of the pixel, get rid of this, so it's a little less confusing. And then here, already tucked in, you have like a default compute shader. And then you want to kind of switch the mode from vertex to compute. Then you want to switch the. So here you see this error: compute shaders require GLSL 4.3. So that's why on a Mac it's not going to work because the version of Mac is like limited to 4.10. So I think at the moment Malcolm is like kind of holding on the Windows-only feature before he switched the whole pipeline to using Vulkan instead of OpenGL, and this way everything will work on the Mac as well. So I'm gonna do 4.3. And now you can see you have all these kind of extra extra parameters. So one thing you can, so for comparison, I'm gonna also create a regular GLSL shader, so fragment shader. Okay, so now I'm gonna just do a little drawing to explain some things. So in a regular fragment shader, so this is kind of my grid of pixel. So all the pixels are executed in parallel, and it's the only unit you're like working with, the pixel. In a compute shader, there is a subdivision. So there is this notion of work groups. So for example, you could have 2 by 2 work groups in X and Y. And then in each work group, and then so if I kind of divide again, 1, 2, 3, 4. One, two. So if you want to write 16 by 16 texture, you could have 4 work groups. So that's my, and each one would handle like 4 by 4 pixels. And then there are like some special features that you can use within the work group. But so it makes the setup of the shader just a little more complicated. So if I go to this one, so dispatch size, so that's the number of work groups. And inside the shader, local size, so that's the size of the work group. And so it can be 1, 2, or 3 dimensions. And so when by default, when you work with texture, it's gonna 2-dimension make sense. And so by default, the texture is 256 by 256. So you can see that if I, and by default it's 64 by 64, but actually you will only need, 32 by 32, because 32 times 8 is 256. So if I go lower than that, if I go 16 by 16, now you can see it's only writing 1/4 of the texture, and that's because all these pixels know the shader is not executed on them. So you always want to set up some kind of dynamic way to do the dispatch size, so you're writing the whole texture. So I'm gonna go back to 32. Then another thing we can notice is that, so to write the pixel, it's using this image store function. And the image store takes 3 arguments. So the first one is the buffer. So I don't know if you've worked in the past with multiple color buffers, but here you can see by default is 1. But if you have 3, so in the fragment shader, so this is the first buffer, and you would need to like declare 3 more buffer with 3 more variables, and then you would write them. But here, you just need to change this number to like the number of the buffer you're writing. So we're gonna do a quick, just to demonstrate. If I copy paste this, I'm gonna do 1. And here I'm gonna do a vector 4. So 1, 0, 0, whoops, 0, 1. So first, if you only do 1, then you get an error. And the error is array index out of bounds because it can't write to the second buffer because it doesn't exist. So I'm going to go back to 2. And now the way you select the other buffer is using a render select. You select the top. And so the buffer index 1 is the second buffer since we like start counting at 0. And we get red. And then you see the second argument. So that's a 2D coordinate. And so one thing you can do in Compute Shader is that instead of each pixel writing only to its location, it can write to another location. And so just to demonstrate, maybe I'm going to start kind of switching to this. Oops. And so here, if I just add an offset, so I'm going to add 50 and 100 and compile. So you can see my white square has shifted by 50 pixels in X and 100 in Y. And so that's because we tell him to like kind of write here and not like just replace the pixel that were processed. So most of the time we're not gonna use it, but there are some a couple of like interesting use for this. So I'm gonna remove that. And the other thing is this. So I-vec2, that's an integer vector. So you have to, and the coordinates are in pixels. So this goes from 0 to 256. So you want to give like, instead of normalized coordinate, like when you sample texture, you need to give a pixel integer coordinate. So now I'm going to explain. So this GL global invocation ID, it's a 2D coordinate that kind of gives you like an ID that's going to be different for every thread. So one pixel per thread. And so if we so if you want to know the various predefined variable, there is this the wiki on the Chronos website. And so you can see you have all these different variables. So the number of workgroups, that's going to be the dispatch size. So it's a way to query it inside the shader without having to like define it as a uniform. And then you have two different kind of ID for each pixel that's executed. And so yeah, so if I go back to the website, so local invocation is going to be an ID within the workgroup, and global invocation is going to be an ID overall the kind of unique, taking into account which workgroup is executed. So it's just a shortcut. So global invocation is just a shortcut for the size of the workgroup multiplied by the workgroup ID plus the local invocation. So I'm gonna go back to the little drawing. It's gonna make more sense. So if we take this pixel, the local coordinates are gonna be 0, 0. And the global coordinates are also gonna be 0, 0. But then if we take, let's say, this pixel, so the global coordinates are going to be 0, 1, 2, 3, 4, 5, 6. So it's going to be 6 and 0, 1, 2, 3, 4, 5, 6. Oh, sorry, 0, 1, 2, 3. So it's going to be 6 and 5. but then the local coordinates are within this work group, so it's going to be 0 and 2. Seven, 4, 5. So it starts at 0. So it's 0. It is 6 and 4. Yeah, sorry. Thank you. And so then you can see that. Oops. So in this example, the workgroup size is 4 by 4. And so this workgroup ID would be, so the coordinate of this workgroup, would be 0 and 1. So this one is 0, 0. This one is 0, 1. This one is 1, 1. And this one is 1, 0. So if you multiply 0 times 4 plus plus 2 sorry, 0, 1. Yep.
It's not the same size when you count the pixel beginning from the top left, but when you count
Yeah.
it's beginning from the bottom left.
Yeah, that's completely right. I should begin from the bottom left in both cases. So these coordinates are, very, very good point. So, okay, I'm just gonna do it again quickly the right way, so it makes complete sense. So if you start from the bottom left, so this one is so the local one are 2, 0, 1, 2, and 0, 1, 2, and 3. So, yeah, and here it should also be 1 and 0, because it's first the x coordinate and then the... So it's going to be 4 times 1 plus 2, so you get 6. And then the other one is 4 times 0 plus 3, so you get 3. So that's how you go from like local coordinates to the global coordinates. Okay, oops. And so kind of a easier way to show this is that I can write, I can say the color is equal to I-vec2 the local invocation. Oops, I-vec2 dot xy dot 0 dot 1. Oops. Sorry. No, the color is just going to be a vec4. Yeah, this. And so now you see kind of this little grid. And if you put down, so I'm going to change the output to float. So this way we can display values above 1. And now you can see that the x coordinate so it goes from 0 to 7 and then kind of start again. And that's because the size of our work group is 8. So if you ask for like the local x coordinate is only going to go from 0 to 7. Yeah. And then maybe another thing that's interesting to talk about here. So in the default samples, you see for the fragment shader, it's using the texture function. But for the so I'm gonna copy this one. I'm gonna create a movie file in. Just so we see a little better, I'm gonna choose the oil drums, connect it to the first input. So the first thing you see is, since now the output is 1280 by 720, it's missing like all these pixels. So if I put down a constant chop, I can say my resolution is 1280. Oops. By 720. And then I'm going to say my workgroup size. So I'm going to say local size x is 8, and local size y is 8. And I'm going to put down a math shop. And I want to divide the two. And so you see that I need 160 workgroup in x and 90 workgroups in y. So here I'm just gonna do it manually here. And now you can see I'm like filling the whole texture. And here, so I'm gonna uncomment the line with texel fetch. Comment this. So I'm just like, and so here I get the result. And so the main difference between texel fetch and texture, so there are a few that are worth pointing out. So texel fetch takes pixel coordinates instead of normalized coordinates. So that's why here it gets the kind of global invocation ID. So it's something that's going to go from 0 to 1280 and 0 to 720. And then the last argument is the MIP map level. So in general, you just want the first level. So it's mostly going to be 0. And the other thing is that texel fetch doesn't use the input extend mode. So if you give a coordinate that's like smaller than 0 or bigger than like the size of the picture, then it's always going to return 0. So that's like a important difference. So I think if you're, in general, if you're working with texture and doing like texture processing more than calculation on the pixel, the texture function makes more sense. So just to demonstrate, so with the fragment shader, I'm just going to copy paste the old drum. And comment it. So here, if I was to multiply the UVs times 2, so you see by default, we're going to sample outside of the picture. But here, if I change this to old, it's going to extend like this. If I do repeat, it's going to resample. It's going to move what's over 1 back into the 0, 1 range. Mirror. But if here I do the same, and I do times 2, so same result, but it doesn't care for this at all. So if you do texel fetch, you need to make sure that your coordinate sample within the correct range. And the other thing that's also important So I go back to the fragment shader. If I do 0.25, so now I'm like zooming in the picture, and you can see that um, by default it's like interpolating between the pixel, because that's the TouchDesigner default. If I choose nearest pixel, maybe I'm going to do something even bigger. Maybe I'm going to do 0.1. So now you can see if I do nearest pixel, it only samples the pixel and doesn't do any interpolation. And so the TextLFET version, it doesn't do any interpolation. It's always gonna give you the center of the pixel. So I'm gonna also demonstrate here. So if I do 0.1, oops, I need to do, sorry. So it's gonna round it to integer. Yeah, I think he wants. So here you see it's pixelated, and even though where I can interpolate, it's not gonna do anything. So these two differences, it's like, so it's not only you sample using the pixel coordinates and not normalized coordinates, but also you don't get the interpolation and you don't get the clamping modes. And so what if in a compute shader we want to do use the texture function? Then we need to calculate. Oh yeah. So first I'm gonna. So instead of using texel fetch, I could be. Oh, I just want to use the texture function. And vuv.st, just like in the fragment shader. Now it seems it's working, but it's not. It's giving you an error. Because vuv, it's a variable provided by TouchDesigner, and it's not defined in the compute shader, so we need to calculate it ourselves. And so the way we're going to calculate uv, which are these normalized coordinates that go from 0 to 1, we can take this global ID. So we're going to create a vec2 that's called uv. And so here the thing, it's like, it seems like a detail, but it's pretty important if you're like trying to do a specific algorithm, or it can like mess you up. So global invocation, it goes from 0 to the pixel coordinate. But when you use texture, you need to sample the center of the pixel, and so you need to add 0.05, and then you're gonna divide by the total resolution. And this way, 0.0, so 0 is like the left of the pixel, 1 is the right of the pixel, and the left of the next pixel, and so 0.5 is the middle of the pixel. And we can use one of the built-in uniform. So utd output infos dot res. Oops. Yeah. So instead of if we use one of the building uniform, we can multiply and do dot res dot xy, and that's because in xy it's the inverse of the resolution. And I think I got it wrong. Utd outputs. And so this comes from the help. So if I fire the wiki and go to write a GLSL top, and now you can see for the output info of the texture, use this uniform. And it's a TD text info. And so TD text info, it's got a res member, and the first two members, so x white, is is the inverse of the width and the inverse of the height, and then you get the width and the height. And it's going to be more. It's always more efficient to do multiplication than divisions, so I can just multiply by the inverse, and then the same than dividing. And so now I like recreated the kind of VUV that's provided. And now you can see that now it's exactly the same. If I do 0.1, I get the interpolation and the and so I think, yeah, these are like all the kind of, oh yeah. And one last thing is that, so by default, so one thing that when you switch, you see there is also this clear output option that becomes available. So as we've seen, each pixel doesn't have to like write over itself, and so you can have some like pixels that don't get any data. And so if you don't clear output, so I'm gonna do again. Okay, so first I'm gonna leave it on, and I'm gonna add like a little offset to the UV coordinates. So I'm gonna do vec 2.5. Yeah, no, sorry, that's not what I want to do. What I want to do is add an offset in the position I write in. So I'm gonna add so here you see these empty pixels. And so now if I was to kind of go back, push even further, like here you see, since every frame is like querying everything, you get this. But if I was to like turn it off, and I remove, maybe, I'm gonna split my screen again. So now if I, oops. So now you can see it's not clearing the pixel. So this is what was previously written. And if I like offset it again, so you can, so basically what you can do is you can do a feedback just inside the compute shader without having to use a feedback top and a loop. But there are some cave hits, so I will like go over it later. But that's just what this function do. And this is not free. It's like another extra thing that TouchDesigner has to do. So if you're sure that you're gonna override every pixel, you can like leave it off, and that's gonna be a tiny bit faster than if it's on. But you need to make sure that you're. And when it's on, you can also kind of change what would be the background. So if I do this, then the output is gonna be cleared to red every frame. Okay, so these are all kind of the basic differences between the fragment shader and the compute shader when you're just doing like 2D texture processing. So you can see like so far it's mostly kind of complicating our life. So if you're not using any of the compute shader feature, then there's no point in using them, because the speed is exactly the same, and it's just easier to kind of make mistake, and like takes more time to set up because you have to set up the display size. Oh yeah, and the last thing, this output access. So the idea is that when you do this feedback and you disable the output clear, you could both read from the texture and write in the same frame. In my experience, this option doesn't do anything. It doesn't make any difference in performance or in what the result is. So I'm not sure if it's just like something in the NVIDIA drivers that doesn't take it into account. Because a lot of times it's like this is something that's declared at the beginning of the shader and Touch does it for you. But maybe the driver just doesn't take it into account. Otherwise, it should optimize how the work is done to like make it faster. So this you can mostly disregard. Um, okay, so now okay, so I'm gonna just create a base and move on to the next. Oh yeah, so just one kind of quirky use for this is technically you can like you could use the compute shader mode as like a pixel drawing tool if you want. It's and I've seen like a cool example of someone doing that. I think it's on the just very quickly. I'm gonna. Oops, that's not gonna work. If I go on the forum and do compute, compute shader. Maybe in the tux. Um, no. Well, yeah, I'll look for it when we take a break, but it's not very. Oh yeah, this one. So this is kind of fake 3D effects, just using the image store and kind of offsetting the pixel. I think he also has a nice. If I. So it's like every frame, you kind of like do this raise and then like offset where the output is going to be written. So it's like a quirky but fun use of the compute shader more as a drawing tool. Okay, so now I'm creating a base and putting everything in. And I'm gonna create a new container. So we're gonna use the arcball camera, so that's why I'm creating a container so we can interact with the panel. For now, we're just gonna go inside. And so one thing I discovered, compute shader. One example when it's really great to switch from fragment shader to compute shader for like doing the same thing is to write 3D texture. And the reason is that when you write a 3D texture with a fragment shader, it's gonna write, instead of writing all the slices at the same time, it's gonna write them one by one. But when you're doing it in a compute shader, it's writing every voxel at the same time. So it's like a 5 to 6 time speed up. So just to show you quickly, first we're gonna do a 3D texture in a top, just using a fragment shader. So what you want is instead of 2D texture, you do a 3D texture. Then we're gonna change the depth. Maybe I'm gonna first define a texture size. So I'm gonna do res x. Let's do 64 by 64 by 64. and I'm gonna call this text res. I'm just gonna do a reference so we can change it later. So you get the X and Y resolution on the common tab, but then you get the Z resolution on the GLSL tab, since it's like only for the GLSL tab. And so now you can see my texture is 64 by 64 by 64. So now just a very easy way to kind of populate 3D texture is to use the built-in simplex noise function. So yeah, so I'm gonna say float noise equals TD simplex noise. So simplex noise, if you look at the help, there's multiple versions of the function. So you can do it in 2 dimensions and give it a vec2. You can do it in 3 dimensions and give it a vector 3. And you can do it in 4 dimensions and give it a vector 4. And that's kind of the same when you do noise stop and you have the option between 2D, 3D, and 4D. So here we want the noise to be like different for every voxel. So we're gonna give it a 3D vector. Sorry, I was doing this. And the nice thing is VUV. So most of the time you just use the first 2 coordinates, but it's actually a vex 3. And the third coordinate is a normalized coordinate in the depth. So I can just do this and then say that the color is going to be a vector 4 with my noise value and save this. And now, so now it's showing us all the slices. So that's why you get all this like tiny square. Each one is a Z slice and then X and Y. So one thing is that now you see the displaying the values doesn't work anymore because it's only work for 2D texture. And you can see also that if I was doing a top 2, it doesn't work anymore because it must be a 2D texture. So if you want to examine the value, you can do it very simply. You can do a GLSL, another. You can do another GLSL top. And here, so here we're going to give it 3 coordinates. So this time we're sampling a 3D texture, so instead of a 2D inputs, the uniform we want is 3D inputs. Because even, yeah, just to show it, if I save like this, it's still gonna complain that 2D inputs is undefined because the input is 3D. So I need to do this. And now you can see that it wants a vector 3 because we're sampling a 3D texture. And now what you can do is define a uniform that is going to be the depth we want to sample. And so we're going to do a vector 3. And the third coordinate is going to be u depth. I'm going to save that. And now I'm defining. And now you can see that going between 0 and 1, I can like move through the texture in the depth. And once you're there, then you have a 2D texture and you can again display the values and sample them from the top too. And if you want to, so same as in 2D, you get free interpolation in the depths. So if you want to sample a specific slice, either you can calculate it and use texture, or you can use the texel fetch function. But here, since it's 64, if you want a specific slice, so it would be float depth. So it would be u depth plus 0.5. Again, so we're like right in the dead center, in the middle of in the center of the pixel, and divide that by UTD output. UTD output info. And now, if you remember, in res we only had XY, and so they store in depths. Again, they store the inverse depth and the depth, so we can actually multiply by depth.x. And I made a mix. Oh yeah, UTD. Oh yeah, it's for the rest. Okay. Tuck. And now we're gonna use this new variable. And so now 0 is gonna be the first slice. What doesn't work? What?
That bug. It's the text editor bug. I don't think that made it into your buffer.
No, it's in an old. No, I think it did. Just as a quick debug, I'm gonna display my depth value. Why is it 0? So now I'm gonna display this guy. In rare cases, I get bugs where like the uniforms are not filled, and this. So let's see. Oh yeah, so you can see when I display this, it gives me 0. So let's see if I. I'm gonna check the help very quickly, but. Oh yeah, so this is a 2D texture, so the depth is 0, and what we want is not the output info, but we want the info from the connected texture. So this is a silly bug. What we want is, I think it's this one. So UTD 3D infos 0 x. Still 0. Oh yeah, because yep. But now it's gonna. Oh yeah, so now you can see it works. So first slice, second slice, and all the way to 64. And then you can see it loops back, and that's because so the W is separate. So by default it's 0 on UV and a repeat on W. I'm not sure why, but so if you do 0 on W, you can see that I'm sampling the depths between slice 0 and 63. And so when I do 0.5, it's like interpolating. So I'm gonna save my file, because then I'm gonna save it more often. Yep. Yes, because I'm still using the texture function. It's just that to make it possible to sample a precise slice, I'm calculating the coordinate for slices using this formula, but I'm using texture. So there is blending. So this way, yeah, it depends what you want to do. Because the thing is the other thing I could have done if I'm not interested in blending and I just want to like examine the values, I could do so I could do texel fetch. And I would do a vex3 of GL frag coord dot xy minus vec2 0.5. I think that's core and yeah. So I need to add also the third argument, which is the mip map. And it needs to be an ivex3. And now so now it's the same but using the texel fetch. And now you can see that if I do oh yeah, so it's I guess it's rounding because you can see yeah. So yeah. So from 5 to 6, no change. 6, new slice, no change, new slice. So using texel fetch now, I don't get any blending. And so again, the devil is in the detail. So GL frag coord, maybe you know it from Shader Toy. So it gives you the fragment coordinates in 2D, but it gives you the centers of the pixels. So it actually gives you coordinate 0.5. So here it doesn't really matter, but to make sure, because the ivex3 is gonna kind of do a floor, and so gives you the just get rid of the 0.5. But just to make it like more explicit, I subtract it. Okay, so now to see how much this is costing, I'm just gonna add a simple. I think I just need to add any uniform and put down a. Oops, what I'm doing. So now it's cooking every frame, and we can see that it's 1.5 millisecond for the texture, which is like, so you have like 16 milliseconds if you want to run at 60 frames. So 1.5 is like a lot. So now we're gonna do exactly the same in a compute shader. So I'm just doing quickly. So we're gonna use again work group size of 8 in the 3 dimension. So again, just to make it flexible, I'm gonna define it here. And I'm gonna put down a math shop. And divide. And so to get 64 texture, of course, we need 8 work group, and each one is 8. And here, so I'm gonna call this D size for a dispatch size. And just to make it clearer, I'm gonna rename this to D size X, Y, and Z. And now I'm gonna reference this. So again, we want a 3D texture. I guess I could have copied the other one, so I'm just gonna quickly reference this. Okay, so now it's gonna spit an error even before we do anything, because when you write to a 3D texture, image store is gonna take a IVX3 argument. So again, I'm gonna get rid of the fragment shader and edit the compute shader. Oops. So if you don't define the local size for any dimension, by default it's going to be 1. So what we need to do first is to define a local size in Z. And that's also going to be 8 because we said it was going to be 8. And now instead of IVEC2, we're going to do an IVEC3. And it's going to be X, Y, Z. And now it compiles correctly. And now I'll just do the same. So now one thing I kind of like to do, just so I have like flexibility between using texture or texel fetch, is to always define UVs. So we're gonna do what we did earlier, but in 3D. So first I'm gonna define a vec3 that's gonna be global invocation. Yeah, maybe I'll just do, okay, vec3 UV. That's gonna be global invocation plus vec3 0.5. So now the thing is, yeah, and we can do multiply a vec3. So it's going to be UTD output info dot xy, and the third dot res dot xy. Sorry, and the third coordinate is going to be UTD dot output dot info dot depth dot x, and save that. Now I can do float noise equals TD simplex noise, UV, and color equals vec for noise. So now we're getting the same output as we had previously. And so now I'm also gonna just put a little expression so it cooks every frame. And so now we can see that we are at 0.1. So I'm gonna make a copy because sometimes when you middle click and you ask for the GPU cook time, it's gonna give you incorrect result when there is only one. Something to do with the waiting for the end of the frame. So just so we get like a little more accurate result. So you can see this one is really 1.4. And the new one is really 0.1. So that's like 10 times faster. And so that makes like a pretty big difference, especially when you want to do a 3D fluid simulation and you have 20 iteration on like a 3D texture and like a big loop. So that's kind of like what motivated me to start the whole 3D texture experiment again, because it's like a lot faster. So now we're gonna stick with the compute shader to continue. I'm just gonna remove this. Gonna remove this one. And gonna remove this one, and also I'm gonna remove this. Just to have a little more control, I'm gonna create a U-scale uniform. And instead of just taking simplex noise of UV, I'm gonna, maybe I'll do U-scale and U offset. I'm gonna create a vec3 which is gonna be scaled, maybe transform UV. And so it's gonna be U scale times UV plus U offset. So uniform vec3 U scale, uniform vec3 U offset. And I'm gonna use this new coordinate and save that. So if we put this to 1, we're back to where we were, but now we can like scale the pattern a little bit, and we can also offset it and animate it if we want. So I'm gonna do this and save this. Okay, so now we have this like nice and fast 3D texture, but how do we display it? How do we render it? So the technique we're going to use is called Raymarching. If you played a bit, also again with Shader Toy, you might be familiar with it. So there are like different versions of Raymarching. I'm gonna try and do a better drawing this time. So that's your camera looking at the scene. That's like a top-down view. That's our texture. And so what we want is, we want to start at the beginning. So we're like shooting a ray from the camera. We want to shoot a ray at the texture and traverse it. And we want to start at the beginning of the texture and then do like little steps until we find, so that's my density, until we find a surface. And when we find a surface, then we color the pixel. So just as a side note, in Raymarching, what people are using is called it's distance field Raymarching or sphere-aided Raymarching, because instead of Raymarching a density texture, they're Raymarching kind of sign distance field. And when you're dealing with procedural sign distance field, anywhere, so this is like anywhere you kind of know, I'm just gonna do it like this. Anywhere the field gives you a value which is how far the closest surface is. So instead of taking uniform steps, you can take like much bigger steps and always use the value of the distance field to know that you can take large step and not miss the surface. Because here, if you were to just take like, sorry, step, like if I was to like start here and then like do like only 2 steps, then I would completely miss my surface. So I need to take steps small enough to find a surface. Okay, and so the way we are going to do this is we want to start at the beginning of the texture and stop at the end of the texture, because we know that's where all our density is, all our values are. We don't need to start right at the eye position, the camera position. So kind of easy to understand and classic way of doing it is to render a cube. First we render the back faces of the cube, and then we render the front faces. And when we sample the back faces, that's like, and then we can like find a direction between the front face and the back face, and that's going to be our ray direction. And we know when we are inside the texture and when we are outside. So that's what we're, I don't know, wait, this guy. So that's what we're going to do now. So I'm going to set up geocomp. It's just going to be a box. And just for simplicity, I'm going to add colors. So the colors are going to be, so when we're dealing with a texture, if we're using normalized coordinates, so they go from 0 to 1. And by default, here we center, so we go from minus 0.5 to 0.5. So in the color, we're going to use the point position, but we're going to use a 0.5 offset. And this way, because we're going to do the Raymarching in texture space, we're going to traverse the texture in texture space. And so this way, we're going to know that our intersections ray with the boxes, the coordinates we're going to get are going to be between 0 and 1. And so we don't have to like transfer them or do anything. So we're going to start like this, just for simplicity. So I'm going to render this. I'm going to call this one back face GO. I'm going to set up a render. So now I'm going to set up arcball camera. So if it's in the palette, it's in the tools, arcball camera. So I'm just interested in the camera. I'm going to go inside cut the camera, get rid of this, and copy paste. And now I'm gonna set up my view. So on the right pane, we have a panel viewer. I'm gonna assign a constant to my geo. So the nice thing is then it's just using the colors we specified. Put down an out top. Disable the back view. And now I just need to go one level up on my container. I'm gonna set the width and height to 1280 by 720, which is the size of my render. And the look, for the background, we want the out one. And one last thing is on the panel, you want to activate middle and right. And this way I can not only rotate, I can also zoom in and pan. Because by default, then you can only rotate but not do the other stuff. Okay, and so now what we want is to render the back faces. So in the constant on the command tab, curl face, instead of use render setting, you're gonna choose front faces, because curling is the face it discards. So in general, curling back faces is like an optimization, because it gets rid of the back faces and doesn't have to render them. In practice, it's not really useful because they get discarded, I think, by the fragment shader during depth testing. But in that case, we just want to keep the back faces. Now we're going to do the same, but this time we want to render the front faces. So I'm just going to duplicate. I'm going to call this back face top. Constant back face. Gonna put the camera here. I'm duplicating the geo. I'm gonna just rename it front face. And renaming this front face. Oops. And here I'm just going to use render setting and rename this front face. And of course, you need to only render the back face here. We can get rid of this also. On the front face, only the front face. So that's what you should have. I'm kind of I'm going a little fast, but if you have like questions, feel free to. And so, yep.
So I was just wondering, why are we doing this front face?
So if I so here, since the color on each face it goes from 0 to 1, and so if I'm going to make a bigger one, but new. So that's the 3D texture. That's the camera. So this is a top view. Oh yeah, maybe I'm gonna turn it a little so it's easier to. So So that's our camera. This is a top-down view. So this is kind of like I guess when I'm using the if you go to the geometry viewer, okay, so this is our top-down view. So this is what I'm representing. And so what we want to do is, so this is the kind of 2D projection, and so from the camera we want to shoot rays, but we want to skip all this, and we want to only start the raymarching here, and start here, take a little step, take another step. So what we need to find the direction of this vector, the start point, and the end point. So the end point is going to be I guess I have to put this guy. So if we go back to this view, so the endpoint is going to be the color we get here for every pixel. So that's going to be this. And the front and the color here, that's going to be the coordinate here. And then we have everything we need, because we have the endpoint and the start point, so we can calculate the direction, and we know where we're going to be inside the texture and outside the texture. If it doesn't fully make sense, maybe when we do it, it's going to... so that's the idea. And so now the first kind of easy way to do it, we can do it in a GLSL top. I'm gonna so we're gonna say x3 ray stop. So that's gonna be the pixel value we get from the. Oh, one thing I forgot. No, I think it. Yeah, no, that's good. Yeah, I think one thing we need to do is to switch to 16-bit float. Otherwise, we're gonna be a little short on precision. So let's do this. Yeah, I don't know why I got rid of the texture DD because I'm needing it. So I'm gonna do ray stop is the first input dot xyz, and ray start is the second input dot xyz. Okay, so now there's like a few different things to set up. Maybe one first thing you want to do is define a macro that's going to be the maximum number of steps. And we're going to set this to 300. Do I need? Yeah. And now we're going to set up the loop. So for every pixel, so first we're just going to use the max steps as a condition. So when you start doing for loops in your shaders and loops in general, you want to make sure you save the file regularly, because if you make mistakes and the loop goes on infinitely, then it's just going to do a hard crash, not even save your file. So you have to. So that's why I'm like starting to do this, So whatever we do, it should always like exit the loop. And so now we want to define a step size. So it's going to be kind of the tiny amount of progress we make when we progress along the array. So and so we're going to define a vector that's going to be our array direction. That's going to be the end of the array minus the start of the array. And now we're going to define a vector which is going to be one step. And it's going to be the normalized redirection multiplied by our step size. So as a rule, since we're dealing with this 3D texture which is quantized, we know we only have at most as many like 64 slices. So if we're in diagonal, so sometimes the idea is we just do steps that are half of a voxel, and this way we get all the detail. And we don't need to do smaller steps because there's not more detail to get. If we do higher steps, then we're gonna start missing some of the voxels and missing some of the data. So for step size, I'm just gonna reference the X resolution and do 0.5 divided by the X resolution for now. Yep.
Can you do a define for the max steps so that you don't blow it up by?
Yeah, just to make sure that if the loop doesn't, because yeah, we're gonna add more conditions so it exits when we're out of the texture, because we know where we're gonna be. But in case there's like something amiss, it's just to make sure it's gonna always stop.
Oh, I'm sorry. Rather than do a uniform, is that
Oh.
are you scared of like accidentally?
Yeah.
3,000 and
Also, yeah, that's also a safer. Yeah. And that also guarantees that if we put a step size to 0, it's also gonna exit the loop. Another way to do it would be also to define maybe a safe step size and to like use this value if the step size is 0. Just like something to make sure your thing is not gonna crash. Yeah. Oh, hi Isabel. Okay, so now yeah, so now we're gonna say float density. Oh yeah, and we need another. So first, so raymarching, you can do two things. You can either, if you're dealing with like clouds, then you will want to accumulate the opacity, kind of like when you're doing fog, and it gets like dimmer and dimmer. Another thing you can do is find an isosurface, and then the idea is when the density is higher than the threshold, that's where your surface is. So that's what we're gonna do, because it's nicer to get kind of nicer shading, and it's also cheaper, because then we stop the loop as soon as we find a surface. Otherwise, you need to keep going and keep accumulating. But maybe we'll do it at the end if we have time. So what we want is we're gonna say, so we're gonna define another uniform, which is gonna be called threshold, and that's the density threshold. I want to do 0.5. So since we're using a noise texture, we can have a continuous value. So 0.5 is just gonna like create the surface when the density is above 0.5. And now we're gonna say float density is equal to. So now we're sampling. The last thing we need is to plug in our density texture. Oops. I'm gonna rename this to maybe 3D noise text, and I'm gonna create a null, and this way we can easily switch. And this is gonna be density top, and we're gonna select it. And that's going to be our third input. And so now, every time we take a step, we're going to sample this texture. So even though we plug in the third input, since it's our first 3D texture, it's actually going to be std3d 0, the first 3D texture that is plugged in. And then the sample location, so it's going to be the start of the ray. And we want to define something called current step, which is going to be 0 at first. And so we want the start of the ray plus the current step. And say if the density is bigger than the threshold, we're gonna define the color here, and it's gonna be 0. Now we can get rid of this one. The color is gonna be equal to 1. And then that means we find a surface, so we exit the loop. And if not, then we need to increment our step a little bit using the small vector we defined earlier. So I think this should work. I made a mistake. So since we're only we're just gonna sample the X because we're just writing the same to RGB X, and we're just we're not dealing with colors. And now, ta-da! So now you get the noise. And now you can see that. So we see a couple different things that seem strange. Is that you can see that it seems it's like continuing, and that's because at the moment we're neither checking whether we have exited the texture or not. We just keep going until we hit the max step. And the other reason is that here the W is on repeat. So even where you're bigger than 1, then you wrap and like you get the other value. So if I put 0, then it fixes it, but that's not efficient. What we really want is to test whether we're outside of the texture and stop the remarch. Also, at the moment, we're not doing any lighting, so we're just saying 1. And you can see little artifacts here. And what you want to get rid of them is to turn off the anti-aliasing. Because when it samples kind of the edges, you just want the exact values and not like interpolate where there's nothing. So now we see we get, oops, nice edge. And one thing that makes the so here you can see it's like a little expensive, 4 millisecond. And now this is purely dependent on the resolution. So if you have more pixel, it's going to be more res. And also the thing is there's no easy way to do anti-aliasing. The only way is to fire more res and then average them. So it would be to like render higher resolution and make it smaller. Or you can also use the anti-alias stop. That helps a little, but it's not perfect. So now to make it a little more efficient, we're gonna add another condition. And so here we're gonna calculate the length of this ray. Maybe we're gonna call it ray length. And now we can test. So every step we can like calculate how far we are. We're gonna calculate the length of the current ray. So it's yep. So now every time we increment the ray, we make sure we're still inside the texture. And oh yeah, length. Sorry. Up. And I made a mistake. Okay, now it's really fast. So, It's probably something silly. I mean, this is normalized. This shouldn't be normalized. I mean, I shouldn't need to be, because if I kind of take this out, it's the same. I'm just gonna check what I did in the wet.
Yeah, it works on mine.
Yeah, oh, it's doing something, yeah, but huh. Oh yeah, sorry. What we want is only this. Yeah, because if I yeah, so restart is kind of this whole thing. So what I was doing is I was like checking the length. So if we were here, restart plus plus the current step was like this whole distance, and what I really want is only check this, and so that's only current step. Yeah, and so now we can see we're like a little faster. Okay, so oh yeah, and the other thing we can see to make sure it's working is that uh, if I put this back to hold, you can see now we don't go into infinity, so it means we're like stop sampling the texture. So now it's like now we want to kind of add a little shading to understand the shape a little better. So what we need for shading is to calculate the normal directions when we find the surface. And so the same as in 2D, in 2D you can use the normal top. And what it does is like an approximation, just calculating the local slope using neighboring pixels. So we can do the same in 3D and calculate the gradient of the density, and that's gonna give us a normal. Oh yeah, also just you can play with the, so you can see if I play with the threshold, we kind of only show like stronger noise value. So I'm gonna, so yeah, so I'm gonna create a new function which is gonna return a vex3, and it's gonna be called calculate gradient. And it's gonna take a vector 3, which is a position. I'm gonna call it post, and also a small value, which is I'm gonna call it's like a small epsilon, which is gonna be e, and that's just like how close from the current point we sample the density to calculate the normal. So we're gonna say, so there's two ways to do it. We can do either central difference. So it's kind of the same on the, if I go back to the normal top method, you have previous and current or previous and next, is whether for like a given sample you take a difference between the current sample and then one next to it, or if you take the difference between the one next to it on one direction and the one next to it in the other direction, just like. So if we have so I'm just doing it in 2D. So if we have this point, we can either take this and subtract it from this, or we can take this and subtract it from this. And you get a little more precision if you do central difference, but you're gonna have to do 6 texture samples instead of 3. So it's a little more expensive. So I'm gonna go with yeah, I'm gonna call maybe let's call right. That's the sample to the right, and it's gonna be so the position plus vec3. So e 0 0 dot x. I'm just gonna copy paste 6 times. So right, left, top, bottom, front, back. So plus e minus e plus 0 e minus e. So we just do it in like x, y, and z. Minus. So I think this is good. And now our gradient is gonna be right minus left, top minus bottom, and front minus back. And we return this gradient. And now once we find a surface, we're gonna say vector 3 normal is gonna be calculate the gradient. So the current position is restart plus current step. And then we're just gonna do 0.01. We can play with the value later, so it's approximate in all cases, so it's gonna give you like sharper or smoother look. You could also base it on the voxel size, so you're like just sampling the next voxel. And this needs to be normalized. So and now we're gonna display this to see what it looks like. And so now you can see that we have something that looks like a correct normal. And so now you can start to see the artifacts from the stepping. So there are a couple ways to improve this. So one way, so right now is that we're only taking regular steps, and once we know we passed the threshold, we could like go backward a little bit, and then forward, and that's called like a binary search. And we could do a few steps of this to like find the exact intersection. And for the normal, if you see if I just use 0.001, then I get like a much smoother result. And then of course it's gonna be so 64 by 64 is not a lot. So yeah, so it's just like the limitation of the technique. And now if we want a really simple lighting, what we can say is that we're gonna call float diffuse. So we can take the dot product with the light. So we're gonna define a light position. Yeah, I'm really gonna do this outside of the loop and do a uniform. It's gonna be U. And so we want the dot product between the light position and the normal, and display this. And we want to clamp that between 0 and 1. And now we need to kind of define so now you can see we have some kind of basic lighting going on. So this is just to show quickly how so I don't know if you're familiar with a kind of lighting model. So diffused idea is you just so if this is your surface, this is the normal, and then if the light is there, so taking the dot product like gives you like tells you what's the angle difference between the two vectors is. It projects the one vector on the other. So when the light is like this, you're gonna see it's gonna be 0. But if it's like facing here, it's gonna be 1. And so we get this kind of simple lighting based on the light position. So this is very wrong and approximate because the position is in texture space, and I call it light position, but what we would want is like a vector between the current position and the light position. But now the nice thing about TouchDesigner is that when you create a Phong or a PBR material, it comes with this nice built-in functions. And so now we're gonna see how we can use the built-in functions, and this way you can use existing lights and kind of integrate this object just using all the lights in the scene, and you don't have to like define custom uniforms and like kind of recreate a whole lighting pipeline for this. But to do this, we're gonna have to instead of just using a GLSL top, we're gonna have to use a matte, because all the so if I'm gonna quickly create a matte and convert it. So all the for the where is it lighting? So we're gonna use the TD lighting function, but for it to work, you need to have the material assigned to an object that's gonna be rendered in a render top, because otherwise, just in a GLSL top, you would have to pass yourself the camera and the lights because none of these are defined. But if you use a render, then it's going to use the lights, the camera, and like kind of create all the uniforms that are needed to compute the lighting based on the scene and the scene hierarchy. So if we look at this, so if we look at this loop, so what we're gonna need is a world space position and a view vector, but we can calculate this using some of the matrices that are provided in the Phong. So now we're gonna convert this to a mat, and this way we can use the lighting function. So the first step, yeah, I guess I can keep, yeah. I'm just gonna, it's none. So the idea is that we're gonna draw a full screen quad and then have like the same code as here, except we will like access to all the built-in uniforms. So I'm gonna do up a new geometry. We're gonna do a rectangle. I'm gonna call that volume GO. And I'm gonna assign the Phong, and I'm gonna create a new render. Render isosurface. And we're gonna connect that to the out. I'm hiding the viewer so it stops. Cooking. So the first thing is in the vertex shader. I'm just gonna get rid of the picking. I'm gonna get rid of this. Oops. Get rid of this. And so, oh yeah, what do we want? I think. Yeah, so we always want the quad to be like facing the screen, and so we don't want to transform it using the camera, the world transform, and all this. So we're just gonna say GL position. I think that can't remember if I need to do another step, but let's see if that works. Oh yeah, so see when I bypass all the transformations and I just use directly P, which is the model space position. So you can see that now when I move you can't really see it, but when I move the camera, it doesn't move, but it doesn't fill the whole screen. And that's because after the projection, all the coordinates are gonna be between -1 and 1. And our rectangle just goes from -0.5 to 0.5. So if we just put the size to 2, now it's filling the whole screen. Now we're going to need to define a sampler, which is going to be the back face, because we still need to do this separate render pass. So this one, I'm going to leave that, and I'm going to add the uniforms we had here. So the step size, the threshold, not the light position. So now first we're just gonna recreate this. So I'm just gonna copy paste all these things first. Just put them here. So it's complaining because here a more clever way to do it would have been to define the sampler 3D as an argument. And this way, this would still work. I'm gonna replace this quickly. Uh, 15. It's gonna be, yeah, sorry, a little sampler 3D texture. That's really what, this doesn't make any sense. Cannot call a non-function. Oh yeah, and texture is a terrible name because it's a function name. So it's gonna be density text. So yeah, so texture is yeah, it's a reserved name, so you can't use it for yourself. Hooray! Yeah, now maybe for now I'm just gonna duplicate this and just remove everything. So we just have the main, and now I can just copy paste from my other function. And now we need to, oh yeah, so we also need to define the sampler as density. And that's going to be the density top. So here we have one more. I'm going to put this at the, I'll just leave it here. So back face and density. So STD to the input 0 now is becoming back face. And the restart, so since we're storing the positions we want in the color, it's just going to be the color we get from the vertex shader. No. Oh yeah. Yeah. I got a little confused. We don't want to do this. We're just gonna comment this again, and instead we want to render a cube. Just gonna render this guy because we only render a pixel where the cube is gonna be, and we want we need the yeah. And so now restart is gonna be what we get from the color we get from the vertex shader. Yeah, and so now of course VUV is not defined, and so we're gonna define UV, and it's gonna be GL frag coordinates dot XY multiply, and the sad thing is the resolution is not defined either, so we need to provide it as a uniform. So we're gonna do vec2 U inverse res, and that's gonna be yeah, so I'm just gonna hardcode it, but it's not a good practice. But 1 over 1280, 1 over 720. So now we have, again, full screen normalized UVs. What else? Sorry, just changing the name. And we're almost there. So SCD3D input now is gonna be the density, and the gradient takes another parameter, which is the density sampler. 70, 74. Implicit guess. Oh yeah, because so as density is a sampler 3D and not a sampler 2D. 74. And here it's gonna be like this. And now, so instead of okay, so now you see we're back. It's black because yeah, so I'm just gonna just put the normal again so we see something. And so now we're ready to use the built-in TouchDesigner lighting function. I'm gonna show this a little bigger if you want to see. Maybe that's a good time to take like a 5-minute break, stretch a little. Um, okay, so I think we're gonna we're gonna keep going. Um, so we have recreated what we had in the simple top, but now we have all we need to actually integrate this with the TD lighting. So I'm gonna copy paste from when I had saved the phone with the lighting, and I'm just gonna use all this. So now in the loop, so I just copy paste kind of the lighting block. So if we compile, it's gonna give us a bunch of errors. So the first thing we need is the world space position of the where we find the surface. So right now, you can remember we're doing the raymarching in texture space, so everything is between 0 and 1. So we need to transform this coordinate into world space. So we're gonna use, so I'm gonna define a vector 3 that's gonna be called world space. And so if you look at the help, there is a whole block of the matrices that are provided for you by TouchDesigner. And so the one we want is just the world, the first one. So maybe I'm gonna, just to make it clearer, I'm gonna say x3 texture space is equal to restart plus current space, so that's where we are. So first we want to convert to model space. So for this we just need to kind of remove the 0.5 offset we added. Because if you remember, so the cube is centered, so the coordinates are from minus 0.5 to 0.5. So if we want to go from texture space to model space, it's just going to be texture space plus, that's going to be plus minus vec2 0.5. And then to go from model space to world space, we just need to multiply the model space position using the world matrix. So yes, I'm just gonna so this part is just to add compatibility with the multi-camera rendering. But then when world is going to be the matrix we're interested in. And so we need to convert our vector 3 to a vector 4 because we're working with homogeneous coordinates, and this way we can have both rotation, translation, and scale in the matrix. But then we're only interested in the XYZ. So we're adding this one just so the multiplication gives the correct result. So now in the loop, I'm gonna replace this by the world space position. And then we need the normal, and the normal right now, same, it's in textures. yeah, so it's in texture space, but translating. Yeah, we don't need to translate it, so we just need to transform it to world space. And so for this, we're gonna use the world for normal matrix, and we're gonna say world normal. So same, we need to do this. And multiply by this. So as you can see, this one is only a matrix 3 by 3 because we don't want to translate because it's going to be the same normals whether you translate them or not. And here we're gonna, I guess let's do world space normal just for, and I'm replacing it also here in the loop. And the last thing we need is the view vector. So the view vector is needed when you want a specular highlight. And the view vector, we can just copy paste what is done here. So if you've ever wondered what this means, so cam inverse 3, so that's the last column of the inverse of the camera transformation, and that gives you the world space position of the camera. So this part is really the world space position of the camera, and then you just subtract it with the world space position that you have, and that's going to give you a vector that comes from the camera to the current point. So that's one way to do it. The other way, since we're already dealing with shooting rays from the camera, we could transform our texture space ray into world space, and that would give us the same result. So I'm just going to do this for simplicity's sake. And now, so 80, yep. So this should be a vex3. Yeah, now we need to define in advance a few variables which are at 0. So we can just define them outside of the loop. And now we're using this. Yeah, we're using color and not outcall. And I'm gonna comment this out. And so now it's black, and that's because yeah, and you want to set the alpha to 1 because otherwise. And so now you can see it's black, and that's because we don't have any light. But if I add a light, ta-da! And now you're wondering, oh, but why do we have this funny rainbow color? And that's because by default, what we copy paste multiplies by the vertex colors. And right now we're using them to transfer the position, so I'm just gonna remove that. So we're like, and so, yeah, so I'm not sure why, but I need to invert just the way I need to invert the normal. And so now the nice thing is that, yeah, I can just I can just move this light, I can also have an ambient light. Yeah. I'm just gonna go full screen on that. I'm gonna put a star here again. And that's so it's gonna be slower because it's gonna kind of do this loop. But I can have maybe a yellow light and a purple light, and I'm gonna move it. Okay, so not the best choices, but just for reference, I'm gonna put a little torus next to it to kind of make sure it's and so you can see that our lighting looks correct and it's matching touch lighting. The other thing you can see is that right now you can't really have both together. The depth steps is still realized on the executed on the cube we have. And so if we want correct occlusion between our Raymarch surface and geo, what we need to do is to manually write the depth of the fragment. And so again, since we have all the uniforms from the camera, we can calculate it ourselves. So there's a nice so Inigo Quiles has a nice article about it. Because this is exactly the same when you're dealing with the distance field raymarching and you want to composite. And so either you kind of go back to the near and far clipping, or you just use the projection matrix. So we're going to do this method just because it makes it's easier to understand. So we're gonna kind of define depths. So by default, we're gonna set it to 1, so everything is kind of behind the camera. And here we can say GL frag depths equal depths. So now the clipping is all the depth testing is all wrong. And so now we're gonna use our world space position. We can do it here. I guess we can do so what we want is to do ourselves what happens between the so first we want to do the projection, so we multiply by the camera projection matrix, and then there's a couple of operations that happens between the vertex and fragment shader that are done behind the scenes, so we also want to do this. So first we're gonna take the camera sorry, I'm gonna start again with my I'm gonna look at the so we want cam proj because we're in world space, so we want to go to cam space and then projection space. Sorry, I'm just doing some So yeah, I'm gonna define a vector which is gonna be ZW. So again, we need to turn it into a vec4. And so since we're interested in the depths, we only need the last two coordinates this is gonna return, which are Z and W. And then so the two things that happen behind the scene is first is the perspective divide. So what you need to do is to so zw.x, so that's going to be z, and you divide that by zw.y, which is w. And the second thing, and so that's going to bring the depths between -1 and 1, and then we want to bring it between 0 and 1, and so we just need to do this. And now, ta-da, you can see it's like properly composited. And so if you want to understand this a little more in depth, there are a few very good resources online. So one of them is this website. So that's kind of the whole pipeline. And so you can see that after the projection matrix that transform I coordinates to clip coordinates, you have to divide by W to get into the normalized device coordinates, and then you have to do the viewport transfer to get the Windows coordinates. And if you want to understand a little more how this works, the whole kind of projection matrix, there's like a whole article on the projection matrix. Not this one. Oh, this one. That kind of explains you how the matrix is constructed, and yeah, what it does. So yeah, so these are the two things that are happening between the vertex shader and the fragment shader that we have to like do ourselves manually. And kind of some just the nice thing is that I'm gonna create a plane. No, I'm not gonna create a plane. So what we can do is we can even cast shadows on our surface from the other geometry in the scene. So if I move the torus a little bit, I'm gonna position my light. So I'm gonna create a new null. The depth you want it to be between 0 and 1. It's after the projection. So it's after the projection. The final value gets remapped between 0 and 1. So the depth is the z coordinate in view space. Then it gets projected, and then it gets remapped between 0 and 1. So when you put down a depth stop, if you don't change the space, what you're gonna get is values between 0 and 1, and that's what is written as the GL frag depth by the shader. So I'm gonna move. Oh yeah. So I'm just moving the light a bit so it casts shadows. And now I can turn on. Yeah, and you just want. I guess you just want the tourist. I'm gonna make it a little smaller. And so now you can see you have since we're using the TouchDesigner lining function, we have even correct shadows from like other objects. The thing you cannot do is the opposite, is have the isosurface cast a shadow on other object, and that's because because we're using this technique. Because what happens for shadows is that the scene is rendered from the light point of view, and when it does it, it's still gonna use this texture which is from the camera point of view, so it's not gonna work. And that's also why if you show the geometry viewer, so I'm gonna hide. So you can see it. It looks all wrong and it doesn't like animate. That's because the back face is always tied to the rendering camera. So there's another technique that is a single pass technique and that doesn't use the extra texture, which is to intersect rays with a box in the shader. And so with this other technique, then you would get correct rendering here, and you would also get correct shadow casting. But we're not gonna get into it. And the last thing with this technique is that another limitation is that you can't go inside it. As long as you're inside, it just disappears. And that's again because this starts clipping. It's when the front starts clipping. And again, with the intersecting the ray with the box in the shader, you can go inside. So there's like a few advantage to the other technique. But the math you kind of need to kind of follow if you just do ray intersection box. So you get like a bunch of tutorial that explains. On the other end, with this technique, the nice thing is that if you reference the so right now you need to make, so if I move this, oops. So you can see if I translate it start to glitch because we need to do the same transformation on our backface geo. So I'm just gonna reference all the transformation. And now I can move it and it's gonna work. I can scale it, and I can even rotate it. Oops. Sorry. Oops. And with the other technique, the ray box intersection, the rotation is a little harder to get going because the intersection is with the min and max of world axis oriented bounding box. So when you kind of rotate it, you get wrong results. But you can work around it. So anyway, just some side notes. Okay, so I guess we have only 40 minutes left. So maybe to go a little further, I'm gonna more do like a show and tell of the other things I had prepared for this workshop. But congratulations on integrating isosurface with the other geometry rendering pipeline. I'm gonna save this. Anyone has any questions? Kind of everything is kind of clear, even if you couldn't like follow along every step.
Is rendering in the box strictly necessary, or is that for performance reasons?
It's just a texture we defined is in a box. So I mean, what you could do is, yeah, you could just render in the whole world and like kind of repeat the texture. But you're not gonna. But all the kind of interesting detail is like in the box, because that's where we kind of define the density, the texture. But yeah, the bigger the surface you're gonna do this technique, the slower it's gonna be. Well, so not with this technique, but with another technique, you could be inside the box and still render it. But then, since you, yeah, but you will need either something smooth like a noise, or a very high resolution texture, because otherwise you're gonna like, you know, if you have a 64 vox 64 by 64 texture, it's gonna be very chunky if you're like really it's inside it. Yeah, so I'm gonna show a couple more examples I had prepared. So I'm gonna open the file I linked to at the beginning. Oh yeah, the other thing I didn't show is again, since we're using the TD lighting function, if you plug a texture in the projector, it's also gonna be applied to your isosurface. And also we did the Fong because it's simpler, but you could do the same with the PBR, and that also works. And so you can get nice PBR and environment lighting on your shapes. So I'm gonna get rid of this because it's not very nice. Okay, so yeah, first thing I want to show quickly. So if we were to do a sphere, I guess I'll duplicate it. And I'm gonna make it a little bigger. So a sphere, I'm just testing the distance from a point with a radius. And you could use, so by default it's really gonna be either 0 or 1. So when you Raymarch it, then you get this very jaggedy result, which can be cool if that's what you want, but what if you want to smooth it out? So one way would be to use so step is the same as doing if something is smaller than something, do 0, otherwise do 1. And you could do a smooth step, and then you could have like a little gradient. And when you have a gradient, then you use the kind of interpolation of the 3D texture, and you get a smoother result. Another thing you can do and which I'm using a lot because when you want to do more complex loops, it's just a nice way to get a smoother result at the end. Is oh yeah, so one thing. Yeah, so the first thing I want to say is that so now you know how to visualize 3D texture, and so they're supported in Touch, but I would say only half supported because none of the tops are going to work with 3D texture. So even if you want to do a simple add, it's going to say, oh, it must be 2D texture. So for every single operation you want to do, you need to create a simple GLSL top and do the operation yourself. So I hope in the future they're going to extend all the tops to support 3D texture. Because one of the nice thing about Touch is to be able to kind of quickly prototype like this like weird feedback loops and see what happens. So it would like make it faster to do. And so for example, if you want to do a blur, it's the same. You have to do your own. So I just did a simple blur. So I'm gonna plug this in. So you can see that with a simple blur, it's the same if in 2D you do a blur and then a threshold, it's gonna give you a much smoother result. Here we would need to like blur even more to get a better result, but it's already better. It's a very simple box blur. So I'm just sampling 3 pixels in one direction and averages them. And then I'm doing this horizontally, vertically, and in the depths, because that's going to be a lot faster than if you were to average a whole cube of pixels. And so then some kind of fun things you can do is if you just do some like silly 2D operations, you can use the texture 3D top to kind of store an history of what you're doing, and then you can visualize it as a 3D texture. Oops. And so now you get this kind of continuously rebuilding itself structure. So the 3D texture is easy to use, but you can't trail. You need to like do a little feedback loop if you wanted to like just have this like continually scroll. And so that's one thing you can do. But then you can also do a whole kind of 3D feedback process and visualize that. So I'm just gonna rewind this. So I'm gonna blur this. So I kind of did this like little funny thing where I'm starting from a sphere, then I'm calculating the gradient, multiplying this by I'm not sure why. Yeah, I'm not sure what this artifact is. Multiplying by the gradient, and like then I'm looping, and so every time, so it keeps like growing this this structure. So this is like a kind of a simpler version of like this one, and this has obviously like a little higher resolution. The viewer? Oh yeah, yeah. Yeah, so you can see you start. So the nice thing is the feedback supports 3D texture. So you can see. So these are like all the slices of the simulations. So I'm just doing. So if we go back to the beginning, there's a blur. Oh yeah, I'm gonna. Here I'm computing a normal, and then I'm using that. I'm computing a noise, multiplying the two, and then displacing my original density using using this noise. I don't know why. So we're just gonna try and get rid of the. Yeah, so just by putting it to 0, I think it was just a sliver. The ray start should be like just a little offset so it doesn't hit the face. So now you can see, looks like this. Yeah, and so you can also plug in so kind of the what I've shown yesterday to detox speeds. So this is using this technique, but now it's like the kind of 2D fluid that people have been sharing. You can extend it to the third dimension, and then you get a lot more interesting shapes. And oh yeah, I forgot to. Sorry. Yeah, I guess. No. Then another thing is that if instead of doing an isosurface, you accumulate density, then that's kind of a nice way to simulate like atmosphere. So here I'm like, where is my? I think I was using the first light. Yeah, so you can see like just this circle that gets projected throughout the volume. If I were to also, and so this, it's using what is called projective texturing, and you can. So yeah, since we're not using the normals and doing any surface calculation in this, but TD provides you with this projection map matrix for the light, and so you can use that to calculate projection coordinates and use this to sample your map, and then you get the way the light would be projected through the volume. And then some other. Oh yeah, we still have like a little bit of time. Yeah, and just to expand on this, so here you can see that instead of interrupting the ray, I just keep adding it and keep accumulating the color. And if you're doing this with color, you have to do what is called front to back alpha blending, because we're like starting from the front and going further and further. And so it's similar to the back to front alpha blending, but a little different. So it's kind of using the alpha would be our density, and the color, and combining them. Here it's just black and white, so you don't really see it. But and then some other. Oh yeah, so another interesting feature is that if you wanted to create a lot of kind of voxelize a particle system, which can be interesting if you want can be used to drive kind of LED volume, and you just want to work in 3D and in a volume texture, and then you would just sample everything. So what you can do is use your threads. Instead of using the threads to write every pixel, you would use one thread per particle, and then you would write to this position in the particle, in the texture. So this looks. So here it's a little hard to see, but yeah, I'm gonna go first to the. So this is a very simple particle SOP. So just emitting with a little bit of turbulence. And so here you can see them in the texture. One thing to see their path better is to turn off clear outputs. And now you can see we're kind of doing these trails in the 3D texture. And we can also blur this and visualize this. I'm gonna reset. And so now you can see it's an extremely fast way of kind of voxelizing a particle system. And that you can also only do in compute shader, since you can write every particle at the correct position in the texture. Because if we were to do it using because if we were to do it using this technique, we would need to loop over every point for every voxel. So you could maybe like have like 10 spheres, but it would start to slow down very, very quickly. And the thing I discovered recently that's like a very new feature is so when you render, I'm going to show this, it's going to be so you can do a very fast surface voxelization of any geometry. And the way you do that is, so here is just a regular torus. So from a regular render, you can now, if you go to the GLSL 1 top, you can turn on image output. And then what this does, we're going to look at the so it creates for you an additional texture you can write to when you're rendering from the main render. And so if it's a 3D texture, it's going to be called MTD 3D image output. And so what we can do is we can do an image store on this variable using world space coordinates remapped to texture space. And then instead of like, it's using the kind of fixed pipeline rasterizer, which is super fast, but instead of just rasterizing to pixels, it's gonna rasterize to voxel and kind of write all this kind of fragment inside the 3D texture. So you can see you get a, so the kind of funny thing is that since it's based on this render and using the camera, it still depends on the camera position. So if I kind of parent it to a null, just so I can rotate. So the thing is that is by default is yeah, the rasterization is gonna in the axis is gonna miss some voxels who are like hidden. And so the funny thing is when you kind of rotate this camera around, so you can see if I render it from the top, from here, now you can see my holes are on the side. So even though you're like writing in 3D to this 3D texture, the position of your camera is still important. And if I was to um, so you see that if I direct the camera to look somewhere else, then it's discarding all the fragments and not rendering to the 3D texture. The step I forgot to show is that to so you need to use a render select, and you select your top, and then you select the image output, and that's how you can get the content of this texture, which is created for you by TouchDesigner. And so this worked for geometry, but it also worked the same for particles. But this is like even like a little faster. So, and kind of some interesting tricks. So yeah, so you can use it as like a fast way of like voxelizing an object and like show it, and you use it as a start for like any kind of feedback simulation. But another trick you can use it for, which I've done recently. So for this render, so I'm gonna open the scene file. Uh, this. Yeah, so I was working on a. Oh yeah, I think this one I really boosted the resolution, so it's even. Let me try this one. Yeah, I was working on a desktop, so I didn't try to make it so smooth on the. Oh yeah. So what I'm doing to create the shadows is that I'm rendering the scene from the light, and then storing the accumulated opacity from the light, and that's kind of so the further voxel is from the light, the darker it's gonna be, because I'm sampling the texture when I'm doing the final render. And so I'm using this new feature because just where the feature is interesting is that if this is my texture and that's my light and that's my camera, so if I was to for every voxel I need to like cast another ray to the light, so this voxel has to try to go through the whole volume before it like reaches the light, and you have to do this for every voxel. But if you do it from the light, you're just accumulating, and so all this so for free you just need to cast one ray to the texture like this. So it's a ton faster that if for every voxel you would have to like do a loop going back to the light. And so now for oh yeah, and in this, yeah, I can also show you very quickly. So this I'm using the single pass. So I'm using the single pass technique, and so you can see that even in the 3D viewer, I still get the correct result because it's not relying on this back face texture. And so, where do I have it? Yeah, so I'm using this function to kind of calculate the intersection point without having to render the back faces. Okay. So now we're gonna change subject in the little bit of time that remains, and just gonna see. So this particle system. So I'm gonna maybe even. So it's just a 2D particle system, just because it's easier to see. So every particle is interacting with every other one. And if I just... So if they all have the same kind of... so it's like a very simple flocking system. It's just creating a repulsion force. And I'm kind of using their mass, kind of like if you were doing loosely inspired by maybe this one. Yeah, so anyway, I'm like using their mass and their distance to kind of compute these forces. And the kind of funny thing is if you it gives you like a nice steepling effect if you use a texture as a... But this is so this is very heavy because the way to do it in a fragment shader is for... So each point is the position of a particle, and I need to loop over every other point. So quickly it becomes very, very slow. And so compute shader, you have a new kind of memory, which is called share memory. So I'm defining it here. And it's very fast, but it's only available... It's like a very small memory. And so instead of just doing a texel fetch for every other pixel, each work group starts by copying their position in this local memory, and then you do your loop on this very fast memory. And so just to compare, so this is with the old technique, and so you can see for 128 by 128, that's 16,000 particles. I'm at like 3 milliseconds, which is quite a lot. And using this shared memory, still doing a brute force algorithm and not using any partitioning or anything. Also in this case, since we're we're interacting with... Each particle interacts with every other, and I'm not even checking on like a radius to interact with. And so so you see it's like twice as fast. So that's and if you were to bump the resolution even more, so let's see when it starts to... Okay. So now it's like I have 30,000 particles. Yeah, so on a faster GPU, you still keep like the difference, but here there is like another bottleneck, so you start to, yes, you see 1.7, 3.5. So it's an interesting boost just using the new features. And just to go over the code, so you can see now I have kind of two loops, and the idea is that I'm gonna do a new. So I'm gonna do again. So this is my shared memory, and so in the first loop, each thread kind of copy its position to the shared memory, and then the current particle kind of compare its position to all these positions that are shared in the shared memory, and then it kind of starts filling it with this one, and do the comparison again, and then this one, and then this one. And so a couple of things that are important. There is the concept of barrier. Because everything is so everything is happening like in parallel, but you don't know, some threads are gonna finish faster than other. You know, you're not sure if like things are you're not guaranteed that everyone is gonna be done at the same time. And so what happens is that if, for example, you were to start the comparison with all the positions shared stored in shared memory before they all like did their copy, then you would get incorrect result. And same when you start copying from the second work group to this shared memory, if some particles are still like in the first loop, you're also gonna get incorrect result. And so what you need to use is this kind of this barrier. And what this says is that everyone is gonna wait to reach this state before continuing. Yeah, exactly. So if you if you're familiar with just doing multi-threading on CPU, that's like a mutex. Yeah. And so just to see what happens if you don't have it. So here you can see it's like. Oh yes, I'm gonna switch back to this one. So it's pretty stable, but now I'm gonna comment it out. And now you can see that you get all kind of like little inaccuracies because particles are like getting their value too early. So that's why you get this like little jittering. So it's not usually, it's gonna depend what exactly you're doing. A lot of time you can, maybe it doesn't matter that much, but you're actually getting incorrect results. And performance-wise, the barrier doesn't really impact the performance so much. So it just
Would it have a bigger impact if you had some paths that were like way longer?
if you do more like a multi-pass thing and you keep iterating, then the kind of the discrepancy would be even bigger.
Would it only go as slow as the
Yeah, I mean you can. If it doesn't look wrong to you and you're happy with it, then whatever. If you want like precise, perfect results, then you need to use barriers. What else did I want to talk about? Oh yeah, because and about these barriers, so one thing that's very important is that you can only synchronize the threads within one work group, and you can never synchronize all the threads in like multiple work groups. And so I don't know, I haven't seen Tim. But so Tim Gerritsen, he shared a lot of time. He uses the kind of not clearing the output and doing a feedback using only a single top. And so as long as you're not interacting, and instead of doing texel fetch, he uses this other function, image load. And image load is just going to load what has been written already to the buffer. So this works fine as long as you're not interacting with pixels from other work groups. But if you are, then you have no, you're going to start getting wrong result because you can never be sure that like after you do the image load and before you do the image store, the image load is gonna be finished for everyone. So you're gonna have this thing called race condition. And so in general, I still stick to the kind of classic feedback loop technique. And the other thing is for this example, I kind of tried separately. So texture fetches, they use optimization and some local cache. So they're going to be faster if you do like a ton of them than image load. So there's other things that to keep in mind. So a lot of time, all this is like very hardware and situation dependent. So if you need to like really optimize deeply your system, you want to make sure you try all the variation and see how that performs for you in your specific case, because it's very very picky.
So when you said the shared memory is being used to cache positions across multiple groups, it's not the work group?
It's so if you look at the loop again, the shared memory is the size of a work group. So it's one work group at a time. So the barrier works because we're only dealing with one work group at a time. Yeah, and so here you can see is that in the inner loop, instead of the texel fetch, I'm directly using this array notation. And this queries the shared memory array. And this is a ton faster than doing a texel fetch. And then the last thing I wanted to show very quickly. So it's using atomic counters. So atomic counter is a special uniform that all the thread can write to. But so if you had one pixel and everyone was writing to it at the same time, the value would keep getting overridden. But the atomic counter is you have special increment and decrement function. And so you can count how many pixels I've written to it. And it's a little slower because obviously it's not like fully parallel because it needs to wait for one thread to kind of write to it one after the other. Kind of an interesting use I found for them was if you have like a 2D picture and you want to emit only from the white part of the picture, like in a classic GPU system, you would just emit everywhere, and then you would kill all the particles. But then, since you have no way to know which particles are dead or not, you're like wasting a lot of texture space. So what you can do with an atomic counter is you can have a kind of every time you find a pixel above your threshold, like white enough, you're gonna increment the counter, and that's gonna define a new position to write to. So that's what I'm doing here. I have this atomic counter that's defined on the atomic counter page. And so since I'm always dealing with 2D texture, I'm like, from this single value, I'm computing y and x coordinates. And then separately, I'm also storing the the value of the counter, because one thing that's very limiting now is that there is no way to kind of query the value of the counter outside of the shader you create it in. So what I'm doing is that I'm kind of doing a maximum to make sure I'm getting the maximum value of the counter, because when I increment the counter, maybe it's going to start here and then go here and then go here. Like, you don't know in which order everything is executed. And so what I want is the value of the last pixel that was written. And that tells me like, oh, in this 248 by 248 texture, I counted I have 1,200,000 pixels that are above the threshold. And so here I'm storing kind of the location of the pixel here. And you can see here that if I use this as my position to instant pixel, then I only have like the white part of the texture. So it's just like and then then you can you could either, so you could use this, and you would know that you could use this as a buffer to emit your particles, and you would know that that would all get born in the white part of the picture. Because one thing that would be nice is if you could use the value of the atomic counter here, but right now, so to get it, you do a top 2, and if you do immediate, then it's going to be pretty slow. If you do next frame, then you have to like delay your texture by 1 frame, and you get like a 1 frame latency. So so that's like just as a conclusion. So in OpenGL, you can do a lot more with compute shaders that you can do in Touch, because in Touch you're really limited to kind of working in this 2D texture and 3D texture paradigm. But so otherwise in compute shader you could use the value of an atomic counter to define how many threads you want to launch another compute shader with, and you can do all this kind of sequence of operation on the GPU without ever going back to the CPU, and changing kind of the number of threads depending on what you're doing. So you can do much more complex particle system where you could kind of have a list of like the live particles, a list of the dead particles, and then like every time you like emit a new particles, like kind of get a value from the dead list. And so those things you would do on the CPU, you can do all these things in the GPU. But all that is not really possible at the moment in the with Touch. So for me, the main use is for 3D textures, where you just get this huge speed up, just switching from fragment shader to compute shaders, and kind of some little specific things like the particle system I showed, and this technique. Okay, so I guess yeah, we're that's gonna be all for today. So it was a lot of pretty specific information. So I hope you learned some interesting tricks, or if you were just curious about compute shaders in Touch, that you're like, oh, I can use this for that, or I don't want to use them, and that yeah. If you have any question, feel free to ask now, or maybe after we break down.